In this video I want to talk about the step response of RL and RC circuits. So for now I'm gonna start with the step response of RL circuit, and then later on I will go over the step response of RC circuit. The reason that I'm doing that is the derivation of the step responses is very similar in both of the circuits. So if you know one, you should be able to figure out the other one as well. So if you remember from before, the step response of a circuit was the result of analysis of the circuit when energy is being acquired by the inductor or capacitor. And that is because we suddenly apply a DC voltage or current source to our circuit. So if you look here, we have a DC voltage source in series with a resistor, we have a switch, and then we have the inductor. So at time t equals 0, this switch goes from the open position to the closed position. So it means that before t equals 0, this switch was open and basically there was no current going through the circuit. But after t equals 0, we have this switch in the closed position, and now we start having current flowing through the circuit. For this analysis, we also assume that the inductor has some energy stored in it too. And this energy, if you remember from before, the energy in an inductor is stored in a form of initial current. So what we have is that we consider I at time 0 to be I subscript 0. So now the question becomes, how can we find out the equation for the current that flows in this circuit or the voltage across the inductor? So to answer this question, what we need to do is we need to write the KVL equation. So let me just quickly write the KVL equation in this circuit. So let's just assume I start from this point, I go around the loop, and then I end up back here. So I have negative Vs plus Ri plus L di over dt equals 0. Or I can rearrange this and have Vs equals Ri plus L di over dt. So as you can see, the result of applying KVL is a first order differential equation. So we have seen before how we can solve this equation by separating the variables. So here the value for Vs, the value for R, and the value for L are known, but we want to figure out the value for current, and we have the current itself and also its derivative with respect to time. So what we need to do is that we need to separate the current and the time, and we have it on both sides of the equation. So that way we can integrate both sides with respect to the corresponding variable and then find out the solution. So this involves multiple steps. So let's just go over the steps. So even though this may look very complicated, but they are all algebraic manipulation until we get to the integral part. So we have Vs equals Ri plus L di over dt. So the first thing that we do is that I put dt di over dt on one side of the equal sign and move everything to the other side. So we have di over dt equals negative Ri plus Vs over L. And then I can just simply calculate the result of this division. It is negative R over L multiplied by I minus Vs over R. Now I multiply both sides of this equation with the integral time dt. So this way on the left side these two will be cancelled. So we are having only di now on the left side, and on the right side we have this equation. Now the last step before doing the integral is to divide the left side, or basically both sides, by I minus Vs over R. So if we do that, on the left side, what we are left with is di over I minus Vs over R. And on the right side, we have minus R over L multiplied by dt. So as you can see, on the left side, we only have the current now, and on the right side, we only have the time. So now that we have this, we can take the integral of both sides over their corresponding variable. So for the left side, it's going to be the integral over the current. For the right side, it's going to be the integral over time. So to avoid the confusion, I change the variables. So for the left side, I take the integral for the current from current changing or starting at I0, that was the initial current of the inductor, to I at any given time t. And then I replace I with x. This doesn't affect the calculations at all. It is only for representation purposes. So we have the x over x minus Vs over R. And I do the same for the right side of the equation too. Negative R over L is a constant, so you can take it out of the integral. For the integral, we have to calculate the integral for time from 0 to any given time t. And again, to avoid the confusion, I change the variable from t here to y in the integral. This is only for representation purposes, and it doesn't have any effect on the calculations. So now, this function to the left, dx over x minus Vs over R, you know that the integral is a natural log function. More specifically, it's the natural log of it minus Vs over R divided by I0 minus Vs over R. So the actual integral, if I just want to give you the indefinite integral, this is going to be natural log of x minus Vs over R. But since we have these two limits for the integral, we replace the x first with it and then with I0, and then we subtract them from each other, and then since it's the natural log, the result of subtraction can be combined as division inside the natural log. So you have seen a similar version when we talked about the natural response of these type of circuits. And on the right side, the integral of dy is y itself. So when you apply the limits, what you end up with is only t. So the right side is going to be negative R over L multiplied by t. So now to eliminate this natural log, what I do is that I take both sides of this equation to the power of e. You know that e to the power of natural log of x is x itself, right? So that means that on the left side now we have it minus Vs over R over I0 minus Vs over R. And the right side we have e to the power negative R over L multiplied by t. And now if we finally rearrange everything and have it on the left side, we have it to be equal Vs over R plus I0 minus Vs over R e to the negative R over L multiplied by t. So there are a few notes that or a few observations that we can have from this equation. So first of all, if you remember from before, we said for an RL circuit we can define a time constant which was L over R. This is true here as well. So if I replace this exponent part is going to simply be e to the negative t over tau, or the time constant being L over R. The other thing that you might notice here is that when the time is 0, this term is going to be 1. E to the exponent of 0 is 1, which means that I at time 0 is going to be I0, and this is actually what we have provided before. So we have Vs over R plus I0 minus Vs, and this is 1. So these two, Vs over R and minus Vs over R, they get cancelled out. So what we're left with is simply I subscript 0. One other thing that you might notice is when you take t to infinity. So when t goes to infinity, this exponential term goes to 0, which basically takes this whole part, this second half, to 0, and then the current only becomes Vs over R. So it looks as if the inductor is not there anymore. And that's actually another thing that we expected from before, that if we have a DC source in a first order circuit and we wait long enough, what happens is that after everything settles down and all the transient responses are eliminated, since we only have a constant current going through the inductor, the voltage across it is going to be 0. Remember, the voltage across the inductor was VL L DIL over dt. So if the current is constant, this derivative is 0, which makes the voltage across the inductor to be 0. And when the voltage across it is 0, that means that it acts as a short circuit. So in that case, we simply have a voltage source in series with a resistor, which means that the current is going to be Vs over R. So this figure shows the graph of the current for the circuit that we have seen in the previous slide. You should consider that for drawing this graph, I0 assumed to be 0. But even if it's not 0, it might look like something like this. It starts from I0 and then goes to Vs over R over time. I0 can even be larger than Vs over R, and it wouldn't matter. If I0 was larger, we should have a graph like this. So now, based on the equation that we have for the current, we should be able to find the equation for the voltage of the inductor. If you remember, voltage for an inductor is L multiplied by the derivative of its current with respect to time. So if IT equals Vs over R plus I0 minus Vs over R e to the negative R over L t, we can take the derivative of this with respect to time and multiply it by L. So the derivative of Vs over R is 0 because it's a constant value, but the derivative of this part of function is going to be negative R over L multiplied by I0 minus Vs over R multiplied by e to the negative R over L multiplied by t. And then to get the voltage, we have to multiply all of that by L. So if we do that and we rearrange the equation, the voltage across the inductor is going to be Vs minus I0R multiplied by e to the negative R over L and t. So the last note that I made regarding the current equation actually holds here too. When t goes to infinity, this exponential term goes to 0, which basically means that the voltage across the inductor goes to 0. This graph is the sketch of this equation, of course with I0 being considered 0, but it also works for other values of I0 as well. So the final value reaches 0, so it doesn't matter where it starts. So now that we have learned this for RL circuits and we were able to find the step response of RL circuit, we should apply, or we can apply, the same procedure to find the step response of RC circuits. For a step response of RC circuit, we follow the same procedure. We derive the differential equation either by KCL or KVL, and then we solve it. So here you see a very basic example of such circuit. We have this current source IS in parallel with R, and then at time t equals 0 we introduce this capacitor to the circuit. So if I write down the KCL at this node, for time t equals t0, we have negative IS plus the voltage here, which would be VC over R plus C dVC over dt equals 0, or if I rearrange that, I get C dVC over dt plus VC over R equals IS. You remember that the current of a capacitor was C multiplied by the derivative of its voltage with respect to time. So now in this equation we have I as a known value, we have R and C also as known values, but the variables that we have, one is VC and the other one is the time. So what we basically do is that we follow the same procedure as before, and we separate the two variables from each other. On the one side we only should have VC, on the other side we only should have the time. And then we take the integral over the specified period, and if we do that, the equation that we find out for VC is going to be like this. VC equals ISR plus V0 minus ISR e to the negative t over RC. Remember, this one was the time constant of an RC circuit. Another thing that you might notice is when we take t to infinity, this term becomes 0 because this exponential part is going to be 0, so this value multiplied by 0 is going to be 0, and VC is going to be IS over R. Because if you remember, we said that over time, when everything is settled down and all the transient responses are vanished, a capacitor acts as an open circuit. So when this is an open circuit, what we have simply is IS going through R, which create a voltage IS multiplied by R based on the Ohm's law. And we have a verification of that here as well. To find out the current of the capacitor at any given time, we can use the characteristic equation of the capacitor, in which the current of the capacitor was equal C multiplied by the derivative of the voltage of the capacitor with respect to time. So if you take the derivative of this equation and then you do some algebraic manipulation, I equals IS minus V0 over R multiplied by e to the negative t over RC for any time greater than 0. From this equation, you can realize that if t is gone to infinity, this exponential term is almost 0, which makes the whole current that goes through the capacitor to be 0. So in this video, we have learned the step response of RL circuit as well as the step response of RC circuits. In the next video, I'm going to talk about the general response of RL and RC circuits.